Thanks a lot, Emil. Yeah, so I'd like to follow many other speakers in thanking the organizers for putting together both the conference and the workshop. I've really been enjoying this, both the conference and the workshop, in particular because it's really bringing together people from all different sides of the field in a way that we haven't seen, I haven't seen as much of in many years as I think would be good for the field. So kudos to the organizers. So I'm going to talk today about F-theory. I've been working with F-theory for some time now. I was actually just looking up, I think my first work with F-theory started almost 14 years ago when Dave and I were in Aspen at the same time, and I was trying to understand 6D supergravity theories. And I'm not sure whether it's embarrassing or not, but I've written over 40 papers since then that have something to do with F-theory. So it's played a really big role in my work over almost 15 years now. F-theory is very interesting and exciting and does a lot of things, but it's also got limitations. And so what I want to do in this talk, I know many of you don't work in F-theory. This is a broad audience, so I want to kind of give a picture for the broad audience of, first of all, what is F-theory, just so we all have some idea what we're talking about. And then I want to say something about what is F-theory good for. It is a very powerful non-perturbative framework, which gives us lots of interesting insights, and I'll talk about a couple of those that I've been working particularly on. And then the main focus of the talk is the last part, which is what more do we want from F-theory? Because, as I'll say, F-theory is actually not really a well-defined theory, even more than, to an even greater extent than the extent to which string theory is not a well-defined theory. And that starts to become a problem as we try to do more and more with it. And so I want to talk about some very specific examples of ways in which, in particular, things like singularities that we want to understand better require some better understanding of what exactly F-theory is. So anyway, what is F-theory, what's it good for, and what more do we want from it? So let's start with what is F-theory. So F-theory, again, is a sort of a non-perturbative formulation of type 2B string theory. I think perhaps the best way to think of F-theory, for me at least in its current state, is as kind of a dictionary between algebraic geometry and physics. And it's a very powerful dictionary, and it goes both ways. Given, as we'll discuss in a moment, an elliptically fibered Calabi-Yau, you can pick out a lot of the features of physics associated with an F-theory construction on that geometry. And vice versa, given a low-energy supergravity theory, you can, in many cases, more or less read off what the geometry is which underlies that theory, particularly in higher dimensions. So the idea is we're going to compactify type 2B, not on a Calabi-Yau, but on some compact Kähler manifold, in general, something which has some curvature. So, for example, projective space in n dimensions. If we compactify on a complex surface, which I'll call B2, we end up with the 6D supergravity theory. And if we compactify on a complex threefold, a complex Kähler threefold, we get a four-dimensional theory. So in type 2B string theory, we of course have the axiodilaton, and there's a nice SL2Z invariance of the axiodilaton. And if we think of the axiodilaton as being dependent on the coordinates of the compact space on which we're compactifying 2B, we have a parameter tau that can be thought of as parameterizing a torus or elliptic curve or a torus with a chosen point. And that can be encoded in a Weierstrass model, which is a simple way of characterizing an elliptic curve, where f and g here are the coefficients in the Weierstrass model, which become functions or technically sections of certain line bundles over the base. It could be B2 or B3. I have B2 here for a 6D model. So the picture is that this Weierstrass model encodes some kind of elliptic fibration over the space B2 or B3. And this Weierstrass model has singularities which correspond to the presence of 7 branes in the type 2B theory. And so we can read off from the geometry of this elliptic fibration, at places where the fibers become singular, we get physics associated with gauge groups and matter and other things. So this in particular relies on a very beautiful, long-standing piece of work by Kodaira in understanding the structure of different singularities that can arise in an elliptic fibration. And at codimension 1, these singularities can be characterized by an affine Dynkin diagram. And the beautiful insight of F-theory from Vafa and Morrison-Vafa's work was to realize that this affine Dynkin diagram is associated with what should be interpreted as the physical gauge group of the theory in the reduced space-time. So codimension 1 singularities, which here, for instance, we have an affine A2, an affine Dynkin diagram is just like your Dynkin diagram for your gauge algebra, but it's got one extra node. And in the case of the A-N series, we just get an extra node that attaches to the two ends. This characterizes this geometric encoding of the gauge symmetry. At codimension 2, for example, where stacks of 7 branes hit each other, we can get higher degrees of singularities. So for instance, here would be a picture where we have an SU3 on this set of branes and an SU2 on this set of branes. And then at the locus where they hit, we get an A4 hat where we get an extra node which corresponds to matter. So at codimension 2, singularities correspond to matter. And there's a whole rich structure of this dictionary that goes back and forth between geometry. Here, all these elliptic fibrations can be described beautifully using the language of algebraic geometry, and this maps into physics. All right, so that's the brief summary of what is F-theory. I'm not defining it, and as I'll say later, part of the issue is we don't have a complete definition, even in the sense that we can define perturbative string theory. Okay, what is F-theory good for? I'm going to describe 2 ways in which I think F-theory is uniquely powerful and has given us some very interesting results. The first one is that F-theory gives us a really global picture of the landscape of supersymmetric string compactifications in a much broader way, I believe, than any other framework that we have for describing string compactifications. And this is most clearly illustrated in 6 dimensions. The set of 6-dimensional F-theory models essentially is one big moduli space, right? There's no superpotential, there's nothing that lifts the degeneracy. So we actually have one big moduli space, which is all connected, associated with different compactification spaces B2, which are connected to one another by blowups and various other kinds of transitions. Different Weierstrass models over each base give us different gauge groups and different matter content. But so we really get one big connected space of theories. And so one way to picture that space is to think of the space of Calabi-Yau manifolds. So this is the famous picture of the Kreutzer-Skarka database. It's a database of 400 million toric hypersurface Calabi-Yaus. We've heard a little bit about this week. It turns out that almost all known Calabi-Yau 3-folds and 4-folds are elliptic. And this is work that we and also Laura and James and company have looked at various different classes of Calabi-Yaus. Of the 480 million Calabi-Yau 3-folds in the Kreutzer-Skarka database, over 99.9% admit an obvious elliptic fibration in some phase, which is to say that there's only about 30,000 where we don't immediately see an elliptic fiber if we look at the toric structure. And these red dots represent, this looks like a bigger fraction than 0.1%, but it's because many of these points are thousands of points. So it's really, the red points are the ones that are the Hodge numbers are the ones that don't admit elliptic fibration. So almost all known Calabi-Yau 3-folds are elliptic. And so this can be thought of as a picture of the moduli space of 6D supergravity, where each of those points represents a different branch of the moduli space with a different base and some stuff over that. I would add that all of these are basically elliptic fibrations over toric bases, and Dave and I some years back listed all the toric bases. There's about 60,000 of them. So one way to think about 6D F-theory is you can make a list, essentially, of all the different bases, and you can even go beyond toric with Yinan Wang. We constructed all the non-toric bases down to about H1, 2, 1 equals 180. So you can basically make a list of models, and that allows you to get a very good picture of this total space, although there's a lot of subtleties. The second thing I want to emphasize is that your typical Calabi-Yau, if we just pick something out of this database, is an elliptic fibration in which there are certain... Please, Alon, yes.
I mean, you say there's no definition.
Yes.
But yet you're able to talk about gauge symmetry.
Absolutely.
So I say that you completely lost. I'm completely lost.
Good. So I would say this is another example of the power of holomorphy and supersymmetry. From the point of view of algebraic geometry, we have this beautiful algebraic geometric structure which is controlled by holomorphy. So we know what the moduli space of Calabi-Yaus looks like, even though we don't have the theory. On the physics side, I think this is controlled by supersymmetry. So I'm emphasizing that we know about supersymmetric vacua. And so each of these, I mean, there are various pieces of evidence that this structure produces a set of theories which match in certain limits with other constructions, such as heterotic, various orbifold constructions and things like that. Even though we don't have a definition of the theory, we have this dictionary which says, associated with a given elliptic Calabi-Yau, there will be a certain gauge group and a certain matter content. And it seems completely consistent that all those are well-defined theories and they all live in one moduli space. These also match, as I'll say in a moment, very nicely with the set of theories that admit anomaly cancellation and all these things in 6 dimensions. And I'll say more about that in a minute. Yeah, good. No, thanks, Alon. Yeah, Shai? No, I'm saying that this covers a bigger part of the moduli space than anything else. I will, in fact, talk a little later in this talk about some cases where this doesn't cover it, and those are puzzles. But I would say this covers a bigger set of vacua in 6D than anything else we know of, and it also does a pretty good job in many simplified cases of covering everything that's even possible, as I'll say again in just a minute. It's not everything, but it's, in certain limits it's dual to heterotic. It covers most things, but not everything. We can talk more about that. The second point I wanted to make is that if you just choose a random Calabi-Yau in this database, you get an elliptic fibration. Typically, there will be a bunch of these rigid factors associated with 7 branes living on loci which have negative normal bundles, which forces curvature that forces the branes to stack up there. So these are called rigid or geometrically non-Higgsable gauge groups. Your typical 6D model has a bunch of E8s, and maybe some F4s and G2 cross SU2s. They cannot have rigid SU5. That's the 6D story. In 4D, the story is very similar. We have less of a handle on the full space. If you come to strings geometry in Hamburg in a month or two, I'll talk more about that. We have a bunch of work in studying the space of elliptic Calabi-Yau fourfolds. Whereas there are 65,000 toric bases for these things, there are on the order of 10 to the 3,000 toric bases, without even including fluxes, for fourfolds, so it's a much bigger space. But the general idea is similar. We have a picture like this. Your typical 4-dimensional Calabi-Yau gives you a big gauge group with a bunch of E8, E7, E6 factors. And the best way to understand this might be that maybe one of those factors, maybe an E7, as I'll say later, includes the standard model, and the rest is decoupled and might be dark matter. But it's a very natural way of seeing a landscape in which your typical vacuum has something which might be the standard model and some other stuff which might be dark matter. So it's a global picture, gives us a picture of how all these things fit together. Let me just say a couple things about the 6D landscape. Again, geometry encodes non-abelian gauge groups. Abelian gauge groups are a bit more subtle. They have to do with the Mordell-Weil group. There's discrete groups having to do with even more mathematically subtle things that the algebraic geometers study, the Tate-Shafarevich and Day-Chatelet groups. General bases have these rigid gauge factors which fit in this list. And so your typical theory has a bunch of factors of these gauge groups in 6 dimensions and in 4 dimensions before those groups are broken. There's also matter, and I'm going to talk more about matter. There are certain kinds of matter representations that are generic, and then some special kinds of exotics that can appear in action. I'm going to talk a bit more about that. So this is an arena in which we can talk about the landscape versus the swampland. And in 6 dimensions, I would say, is the first dimension, starting from the top, where we have a really interesting tension between a really rich set of theories that we can realize that satisfy anomaly cancellation, and importantly have matter living in a variety of representations. That doesn't happen above 6 dimensions. And we have a strong set of constraints on the 6D supergravity theories because we have gravitational anomalies that put constraints on things like the rank of the gauge group. And we also have a good understanding of this F-theory construction. So this is a great arena for comparing the landscape to the set of possible theories and understanding the swampland. So for example, if we restrict to a non-abelian gauge group and limit the number of tensor multiplets to fewer than 9, there are a finite number of branches of this theory. You can just prove that. And so in a sense, we can make a list of theories with T less than 9 and non-abelian gauge group. And in fact, if you look at some recent papers, they include some of these lists. And then we can ask which ones can we realize in string theory or any other approach to, in F theory or any other approach to string theory. There are some interesting cases where it might, or where it seems that there may be infinite families of consistent theories, not F theory, there's a finite number of F theory branches, but there might be an infinite family of consistent theories. There was kind of an interesting series of things where Schwartz at one point suggested an infinite family of theories at t equals 1. We proved here that those were not good. We found another infinite family, and then these folks showed that, ruled out some of those, and then there may be some other infinite families, so there's kind of a back and forth on that. There's also an interesting question about whether there are infinite combinations of U1 charges in the swampland, and there's a whole interesting thing on that. I don't want to go too far into this. There have been dozens, if not hundreds, of papers on essentially what I think Hiroshi called, and I like the term, quantitative swampland physics, where we can make a list of models, very concrete models, and say, okay, either this is a good model or it's not. If it's a good model, we should be able to find it in string theory. If not, can we find some inconsistency or reason why this is a bad theory? Okay, so that's the first thing which I think F theory does for us. It gives us a really good picture of the landscape of string compactifications. Yeah.
How do you know whether something's in the swampland or not?
Well, I would, okay, depending on how you define the swampland, I would define the swampland for my own purposes as something which we don't know any reason why it's inconsistent, but we don't know that it lives in string theory. And so in some sense, you could think of the goal as to clear the swampland. In 10 dimensions, if you put in supergravity, if you put in supersymmetry and gravity, then we've cleared the swampland, right? And if you look at Green-Schwartz, they say there are 4 gauge groups, right? You know, you guys found the heterotic string, and the U1 to the 496 and E8 cross U1 to the 248 is ruled out, actually, because it's not a consistent theory. So, you know, I don't want to debate the definition of the swampland, but I'm just saying there are theories which we don't know how to rule out, which appear to be anomaly free, and we haven't yet found a reason why they're inconsistent. It could be that unitarity or causality or something may eventually rule those theories out. So there are theories which we don't know how to rule out and which we don't know how to get from string theory, and I think those are interesting places to look. This was in my mind, this is what you guys were doing when you looked for the heterotic string. If the swampland is something which is, I don't know what it means to be consistent and not realized in quantum gravity, but things which look consistent but aren't realized by quantum gravity, like the E8 cross E8 gauge group, when you all, you know, looked at that. Okay. Second thing that F theory is good for, I would say, is string phenomenology. So from this point of view, there are a lot of different ways that we could imagine getting the standard model. We could start with a gut, or we could start with the standard model gauge group itself, with or without the mod Z6. We could either tune it, or we could use a rigid gauge group to realize it. And there's been a lot of work on each of these 4 approaches. The original approach that Beasley, Heckman, Waffen, and Augie Weinholt pioneered was to use a tuned SU5 as a gut, and there's hundreds of papers on realizing string phenomenology using those constructions. More recently, there's been a bunch of work. The Penn group and we and others have looked at tuning the standard model gauge group directly. One simple way is through these so-called F11 fibers. It was a paper on a quadrillion standard models. This is the direct tuned GSM approach. So the top 2 approaches are being discussed here. These are ways of getting things like the standard model. I would say that those kinds of models are relatively rare in the landscape because they require fine-tuning a lot of moduli. And many of the bases in the landscape don't allow you to tune that many moduli and don't support those big tuned gauge groups. Another approach might be to take the standard model directly as a rigid group. That's difficult because the U1 factor is difficult to integrate. So right now, my feeling is the most natural approach is to look at one of these rigid gauge groups, like E6, E7, or E8, and realize the standard model is a subgroup of that. So just briefly, I'm kind of happy about some recent work with Kobe Lee, student of mine at MIT, Xingyan Li. This series of papers, we've been looking at starting with a theory which has an E7 that's rigid. In some preliminary scan of a large number of Calabi-Yaos with Yunnan, we found about 20% of the bases supported rigid E7. Some more on that I might talk about at another conference. But E7s are fairly common in the landscape. If we have an E7 rigid gauge group, you can turn on fluxes that break that gauge group. If you integrate the flux, this is through a sort of M theory picture, you integrate the 4-form flux of M theory through a 4 cycle, you get some parameterization of the flux, and you can tune those fluxes, choose those fluxes in such a way that you break some of the Cartan generators, but not all, and you can get residual U1s. So there's actually a fairly straightforward combination of fluxes that you might get randomly that breaks E7 down to the standard model. One way that we've been looking at is using what's called technically vertical flux to break to SU5, and then remainder flux to break the hypercharge down. And there's a whole long story there. I don't want to get into it. If you want to come to the string phenomenology conference this summer, I'll talk more about that. But a couple nice things about this are that proton decay, the dimension 4 and dimension 5 proton decay operators are suppressed automatically in this model because they are not invariant under the E7. So there's kind of a hidden suppression where certain Yukawas, which look okay under this gauge group, are exponentially suppressed by the broken E7. So these are kind of nice models, and it's easy to get 3 generations. You just get some Diophantine equations, which it's really easy to get 3 generations. So I'm not going to tout this model too much. I just want to say that this is the second thing I want to advertise, that F-theory is good for understanding phenomenology. Okay, F-theory is great. We can do all this stuff. Why am I right now actually rather frustrated with F-theory? Okay. You know, dimension 4 and dimension 5 are suppressed. Dimension 6, not so much, actually. So this.
But you break lepton number by 2 units or by 1 unit?
Break lepton number by 2.
In order to break by 2 units, you need the 1.6 of SO10, or it's subgroup.
Yeah, I don't think we don't have that. Let's talk offline about that. I would have to refresh my memory of exactly what's going on there. Good. Let me, I'm running quickly through my time, but let me now talk about what more we want from F-theory. So this is all great, but the problem is we haven't got a complete definition of the theory. So if we take, for instance, one of these standard model constructions and try to actually start computing at things like actual numbers, we don't even have a framework in which, if we had arbitrarily powerful computers, we can imagine getting the correct answer out. There are many ways that people use to understand F-theory. As I said, holomorphy in algebraic geometry gives us a remarkably strong global picture. It's often defined as a limit of M theory. When I talked about fluxes, I was using that M theory framework. Type 2b supergravity provides insights. There's a beautiful Sen limit in which there are perturbative ways of analyzing the theory in certain limits. There's a duality to heterotic when the base is P1 fibered, and we've been working a lot with Laura and James in recent years to try to understand that heterotic F-theory duality better, to understand some questions that are very puzzling in F-theory. String junctions give insights. In some cases, again, related to Sen and Dasgupta and Muki's work, tau is constant, and Shai and collaborator recently have a beautiful paper where they start bootstrapping F-theory based on that. I haven't given references here because there's a zillion papers on this, but despite all these approaches, we have no rigorous definition that would in principle enable us to compute quantitative features. Now, I will mention here that for some years now, Dave has been promising a paper, What is F-theory?, which may answer some of these questions. He recently told me that the title has been amended to What is F-theory, 1, which suggests that it will not answer all of these questions, but maybe some, and we look forward. Great. Yes, we would much rather have What is F-theory 1 sooner rather than having the whole thing go Dave. Anyway, so for the rest of the talk, I want to talk about some specific places where a better understanding of F-theory would be useful. And these, in particular, involve places where there are singularities which are hard to understand from our current framework, or a set of frameworks. Yes?
I mean, just starting from type 2D supergravity with the high degree of corrections, then you want to imagine, well, at least you can describe the solution.
Yes, you can describe the solutions, and in fact, there's some progress in that direction. I mean, for example, you can derive some of the things about the gauge field. You know, actually, this is partly answering Alon's question. You can get some of the information about the gauge fields and matter just from looking at that point of view. So there was a nice paper by Douglas and a mathematician whose name is escaping me at the moment, where they did this for 8-dimensional F-theory, and with Sheldon Katz, we recently generalized that to 6 dimensions, where you can get some of that structure out of 2B supergravity. But 2B supergravity by itself is not enough because there's non-perturbative physics, and in particular, it will not resolve, I don't think, any of the questions I'm about to list. which have to do with singularities. Thank you. Douglas Park-Schnell, yes. And of course, Daniel Park was on that paper too, yeah. Yeah.
If you come a number here with back to tau, we do from the point of view of momentum expansion, that's in principle, can you talk about momentum expansion?
Okay, but tau is varying across the compactification space, and so there are regions where the string coupling is strong.
That by itself is not a problem from the point of momentum expansion. I think maybe the problem you worry about is the variation over.
Great. Perhaps you're right, and by using standard string theory techniques in 2B, we can illuminate some of these questions. Let me list my questions, and I'd love to talk afterward about how they can be, any of them might be addressed, or any other of these questions might be addressed in principle using string theory. It seems hard to me, but you may have better ideas than I do. Okay, so let me go through a few things. Let me say a little bit more about matter, because the next, gauge groups we understand very well from the Kodaira classification. Matter is a little more subtle, and this also comes back to the question of, do we get everything out of this? I'm going to consider 4 kinds of matter representations. First, I'll mention again this generic matter, the simplest kind of thing. Then I'll talk about exotic matter in F-theory, and then I'll talk about exotic matter which seems to be possible in string theory that F-theory doesn't know about, which is an example of something which we just don't know how to see in F-theory. And then there's what I would call swamp matter, which is stuff which is not in one of those 3 categories. So generic matter, you can rigorously define, I should have put a reference to a paper with my former student Andrew Turner, that the notion of generic matter can be formalized by thinking of it as the matter that appears on the moduli branch of greatest dimension where we fix the gauge group. So for instance, if we fix the gauge group SUN, then the moduli space branch with the largest dimension has just fundamental antisymmetric and adjoint matter. And this appears in the simplest F-theory models like the Tate models that were discussed in some of the early F-theory literature. There are exotic kinds of matter in F-theory, including things like the triple antisymmetric of SU6. This can appear in special tuned Weierstrass models, and you can do constructions that we worked out with these folks to reach this kind of matter by doing a sort of a matter transition where you keep the gauge group fixed, but you trade one kind of matter for another anomaly equivalent kind of matter. And in some work following the original ideas of Katz and Vafa, with Clevers and Dave and Nikhil Ragaram, we found a systematic way of classifying exotic F-theory matter. And the short way of describing that is that exotic F-theory matter representations live in incomplete affine Dynkin diagrams. You have to make them incomplete, since otherwise you would have to shrink the entire fiber. So for example, the SU6 triple antisymmetric, which you can think of as having Cartan indices 0, 0, 1, 0, 0, comes from this Dynkin diagram. It's a regular Dynkin diagram where this red thing is the matter and this is the gauge group. Similarly, you can get an SU4 cross SU4 bifundamental or an SU4 symmetric if you have this Dynkin diagram where this is the matter and these are either 2 different SU4s or 1. So just to draw another example, another slightly exotic example is you can get the triple symmetric of SU2 if you have some divisor that crosses itself 3 times with a suitable singularity where it crosses. So we can get some kinds of exotic matter. However, it's been known for some time that there are other matter representations which can arise in heterotic constructions, such as the E7 cross SU2, fundamental bifundamental, and it's unclear how these connect to F-theory. There are some hypotheses, but I don't think anything really compelling at this stage. There's a very nice bit of recent work by Beccara, Hamada, Tarazzi, and Vafa where they use asymmetric orbifolds and construct models with a whole bunch of non-F-theory type exotics, including this 56,2 and the triple, the 333 of 3 factors of SU3. These models have other interesting features which suggest that they can't be realized in F-theory. They have no neutral hypermultiplets. There's always at least one in F-theory. And they violate this Kodaira condition that comes from the construction of the gauge group in F-theory. So actually, I've been working with Beccara, Tarazzi, and Paul Ullman, following up on this. And in fact, we can prove that matter from such asymmetric orbifolds always lives in a complete affine Dynkin diagram. Basically, the idea is you have the Dynkin diagram associated with the original gauge group, the matter will live in a direction which makes a degeneracy in the Cartan matrix. So basically, there's always a null vector characterizing the direction. So you get, that forces you to have an affine-Dynkin diagram. So for example, this is an affine-Dynkin diagram for this. This is an affine-Dynkin diagram for the 333 of SU3 cubed. But these cannot be realized in standard F-theory. You would somehow need to shrink the entire fiber, and they violate various other things. Nonetheless, these live at finite distance in the moduli space. So there should be some way to get there if we really knew how to define the theory. Okay, I'm running short on time. That's one place where F-theory is not quite adequate. Another thing that we would like from F-theory is resolution-independent physics. So much of the physics of F-theory is hidden in the singularities of the Calabi-Yau manifold. And the standard approach, following the kind of M-theory picture, viewing F-theory as the limit of M-theory, after a few dualities and things, is to resolve the singularities and compute. And this is a great way to compute various things, but it hides the idea that the physics should be independent of resolution. These resolutions are unphysical. Those directions of resolving do not exist in the F-theory in the F-theory moduli space. So we'd like to know if there's a more direct route. So an example of this is when you're computing chiral matter, there's a whole beautiful story that relates to the heterotic story that we can get the chiral index of a given representation by integrating the G flux in the M-theory picture over some surface, and this was worked out by a whole bunch of people, and there's a lot of work, there's many, many papers on this. This is just a sampling. The standard approach is you resolve the thing in some way or another, and then you do the calculation. But the answer is independent of resolution. So in some work a couple of years ago with Patrick Jefferson and Andrew Turner, we looked at how to think about this as a resolution-independent structure. It turns out if you take the intersection numbers on the Calabi-Yau fourfold after a resolution, those intersection numbers are topological data that are different for different resolutions. They're related by flops for different resolutions of the same Calabi-Yau. If we organize these as a matrix with pairs of indices as indices to the big matrix, then we can characterize the flux story as the chiral index is some vector of fluxes multiplied by this matrix. And if we take this matrix and get rid of the null space, we get a non-degenerate matrix, which we could call M-reduced. And it turns out that this reduced matrix, that is the matrix of describing the inner product of middle cohomology, of vertical middle cohomology on a general Calabi-Yau fourfold, turns out to be independent of resolution. So this is some mathematically resolution-independent structure which governs the physics, and it's totally not obvious from the M-theory point of view why this should be resolution independent. So there's a question: can we directly construct this kind of singular, this kind of M-red from the singular geometry? And there are some related questions on identifying invariance where the flop is in the base rather than in the fibration. Okay, I'm running short of time, so let me say one more thing. Another place where we might want more, again having to do with singularities, is that there are interesting places where the vanishing degree of the Weierstrass coefficients goes off the Kodaira classification table, becomes 4, 6, and there's no Kodaira resolution. At codimension 1, these are at infinite distance and are unphysical. At codimension 2, this can be resolved either by blowing up the base, or in some cases this can be thought of as like superconformal matter. I should mention there's a whole beautiful story. I gave 2 applications of F-theory. One was to phenomenology and one was to the landscape. There's another nice application, which is the understanding of 6D superconformal field theories that these folks and others have worked on. That plays a role in understanding these codimension 2, 4, 6 singularities. At codimension 3, the meaning is much less clear, but there are many cases where we get an additional contribution to H4 that can support flux. And so with these folks, we've been working on understanding this also with Laura and James in the context of this work on connecting to heterotic. This flux can produce superconformal matter or standard matter. It may or may not break the gauge symmetry. I'm not going to say too much about this because I don't have 100% confidence in our understanding, although we're coming along on that. But we would like a more direct way of understanding these kinds of phenomena. So there's 3 ways in which the singularities in F-theory really resist a clear understanding, in part because of the absence of a full definition of the theory. So I think I'm almost out of time, so let me just summarize. F-theory is a very powerful framework. Arguably, I would say it provides the best and broadest global overview of the supersymmetric landscape and the largest and most natural set of supersymmetric standard model-like string constructions. I'm happy to debate those statements with anyone offline. It is, however, not completely defined. The theory does not see some classes of string vacua and associated phenomena. Geometric singularities can be hard to understand and analyze. We cannot even in principle, and I look forward to you talking more about that, really calculate things that we need to know, actual numbers for our phenomenological compactifications. SUSY breaking is difficult or impossible to analyze because we're relying so heavily on algebraic geometry and holomorphy. So we need some other framework, perhaps some analog, a string perturbation theory or a string field theory, to give us a systematic way of thinking about these questions. And so this talk is really partly aimed at getting people interested in F-theory and understanding better what we might be able to do with it, because lots of really smart people here giving fascinating talks about interesting things. I'm sure some of you will have some interesting insights into how we can do more with F-theory. So I'd love to hear that from anyone who's interested. All right. Thanks.
Question.
I just had a question, actually, in your case where you're breaking these big gut groups down to something like the standard model.
Yeah.
The global choices that you're making for your vertical plus remainder flux, did those reduce on the 7-brane world volume to the so-called hypercharged flux that people were interested in
this one does. The remainder flux does. So we sort of do this in two steps. We use a vertical flux through this formula here to break the gauge group down to SU5. And in order to get the proper U1, I mean, you can do this in various ways, but you don't get exactly the standard model unless you break down to SU5 and then use, there's this funny thing, remainder flux, which is not a vertical flux is a flux which is basically the wedge product of two 1-1 forms. You have to use a remainder flux. So there's vertical flux, there's a whole taxonomy of fluxes. There's a vertical flux, which is a wedge product of two 1-1 fluxes. There's horizontal flux, which is alternatively either sort of the mirror of the vertical flux or it's things related to the complex structure moduli. And then there are things which are neither fish nor fowl, which are the remainder fluxes, which Brown and Colanucci and others have studied. You need those remainder fluxes, which can occur only when the base is non-toric. So we've actually been looking a lot at non-toric bases to understand these things. That was a story that was already understood in the SU5 literature. So we're actually using a similar story after we get to SU5 to what was in the tuned SU5 Beasley, Heckman, Waffa, Donagi, Weinhold story to use remainder flux to do hypercharge breaking of the SU5 down to the 3-2-1.
Thank you.
How long?
So in string theory, we also have the non-supersymmetric vacua.
Yes.
How do they fit into the?
Great question. I think at the end, I said something about SUSY breaking is difficult to analyze. I would love to understand how to think about non-SUSY breaking in non-SUSY vacua in F-theory, but I really don't know. It's a great question. That's one of the limitations, is that the power comes from holomorphy and algebraic geometry, and the limitations come from the fact that we don't quite know yet how to systematically go beyond that. So I don't know. Heterotic is great for getting non-supersymmetric things, and even company have been doing these interesting things with hyperbolic manifolds, which I'm quite interested in. I don't have any idea how those could relate to F-theory or any dual version of F-theory or anything like that. So it's, got something. I think.
Other questions?
Clifford, I think, had a question back there.
Thanks. That was a very nice talk. I'm going to ask a very naive question at risk of offending our mathematical colleagues. I was just wondering, is it possible, just addressing, for example, the exotic things that don't seem to show up, could it be that there are mathematical structures that have yet to be discovered that would fill that in, or is the expectation that we somehow have to go outside the existing framework to complete the story.
Good. So let me comment on two places. I mean, many of the things I was describing are things where F-theory does have the singularities, we just don't know how to resolve those. So it could be that there could be additional mathematical, for instance, I think there should be some version of cohomology for singular manifolds that would address this issue here, this resolution-independent structure. If we could really write down a good cohomology theory for the singular collabia without having to do the resolution, I suspect it would give us these answers. There are other things which we just can't get there from here, and one of them is the thing I mentioned about these non-F-theory exotic matter types, like the 56-2. Another thing is that there are some heterotic compactifications, basically heterotic compactifications on the manifolds that are not elliptically fibered do not have an obvious F-theory dual. So as I said, almost all calabi-Yaos are elliptically fibered, and heterotic on anything that's elliptically fibered will have an F-theory dual. So that's, I would say, most heterotic compactifications, but there are some which are not. I don't know how to fit those in. Those cases, let me speak most directly to this case because I've thought recently most about it. This seems to be something that lives at a finite distance in F-theory, but probably where you have to shrink the whole fiber. So it's probably related to F-theory, and I've been talking to David also a little bit about this. Maybe some slight extension of our algebraic geometric knowledge might help to understand these. We can almost see what they are, but not quite. So I think in some cases, yes, and we might almost have a hint of how to get there. In other cases, I really don't know how to get there from here. And it may be the case that, like the other approaches, F-theory only covers a piece of the moduli space. I would say in 6 dimensions, because it matches so well with the set of available theories, far better than any of the other constructions. I mean, heterotic gives you a bunch of things at one tensor multiplet, but it's very hard to describe things at more than one tensor multiplet. I think F-theory is very powerful in that sense and gives us a bigger picture of the landscape, but it's probably not everything without some major retooling.
Yeah.
Is there any more to elliptic fibration beyond just saying the value of tau over the base, apart from mathematical convenience?
In some sense, once you have defined the value of tau over the base, you've chosen a section of minus 4k, where k is the canonical class of the base, and a section of minus 6k. That completely defines a manifold, which is an elliptically fibered Calabi-Yau. That's the full geometry. Now, F-theory has other degrees of freedom. There are Kähler degrees of freedom and things like that. But we don't have a systematic way of writing down that Lagrangian that includes those other things. We have a clearer understanding. Those are the complex structure moduli. So the complex structure moduli are some of the hypermultiplets that appear in the theories, and those are the degrees of freedom. So to answer your question, I believe that if really all you're asking is what do you need to characterize an elliptic fibration, all you need is the Weierstrass model. To understand it, you need to do more.
But 90 from type 2b, that's already more than what I would have thought you need. Because you emphasize the section, but why do I need a section? If I just specify the value of tau with this SL2Z monotromy, isn't that enough?
You need the section. So there are genus 1 fibrations without a section. And in a paper with Dave, we argue that those actually, if you go down to M-theory picture, those represent F-theory compactifications on an S1 with a Wilson line. So that the F-theory compactification you're looking at would be actually on the Jacobian fibration of that genus 1 fibration. So I think, Dave, do you have another reason why you need the point?
I'll just say that in my upcoming paper, the section will be apparent.
Sorry, the section will be what?
In my upcoming paper, the one he advertised, the section will be apparent. You'll have to have the section. The section of the elliptic. Okay.
Yeah. So again, naively, you can do it without a section, but I would say that would
Give a lecture about my upcoming paper.
Yeah.
Keep dropping in.
In 5 dimensions, for example, if you compactify on something without a section, it's in the same class as what you would get if you took F-theory on something with a section in 6 dimensions and then compactify on a Wilson loop where you turn on something around that circle. So they are closely related. That's in a paper with Dave, and I think Dave is going to say more about that in his upcoming paper. I will not try to eliminate that further.
Okay, maybe one last question, if it's quick.
Yeah, Naomi.
Maybe it's off the topic of the main thread, but in like the shield plot you showed where most of the Calabi-Yaos have an elliptically fibered phase,
Yes.
the 30,000 that you said didn't, were
Yes.
those 30,000 where you couldn't find a phase? Where?
Correct. It was just, we did a really naive scan. So to be more specific, what we did was we took the polytopes, this is with Yu-Chen Huang, we took the polytopes, right, and we looked for whether there's a reflexive 2D subpolytope. And if there's a reflexive 2D subpolytope, you can argue that there's a triangulation which is compatible with a projection. And it's a little tricky because it's not necessarily an FRST triangulation, it might be a Vex triangulation, which I know you guys have thought about also. But there is a triangulation. If we found that, we didn't put a red point. If we didn't find it, we put a red dot. But in many of those cases, I suspect there may be an elliptic fibration. So Lara and James did something similar for CCs, complete intersection Calabi-Yaos. They used sort of a naive way of checking which ones have elliptic fibers. And correct me if I'm wrong, when you guys did a more detailed analysis, when you looked at things that were not obviously elliptically fibered, you found that actually there were hidden elliptic fibrations for many of those, right? So I fully expect that the remaining 30,000 out of 480 million, many of those will also actually be elliptically fibered. Yeah, the quintic. Doesn't have enough H11. Anything with H11 equals 1 can't be elliptically fibered because if it's elliptically fibered, it's got H11 as H11 base plus the fiber. I don't know offhand of any with a simple argument. I don't know. Lara, James, Dave, do any of you have a example that you know of that you can prove it's not elliptically fibered? I mean, you need to, actually, sorry, I think you can in some cases. The way you prove it's elliptically fibered is you find a divisor which satisfies d cubed equals 0 and not d squared equals 0. And so if you know the triple intersection form, I believe there are other cases at larger H11 where you can systematically prove that you can't solve the quintic equation. And actually, we use that in the paper with Yu-Chen. We have a theoretical argument for why, as H11 goes up, the probability that you're not elliptically fibered should go as 2 to the minus H11. And that is matched experimentally. And now I'm over time, so I'm going to stop.
I think we'll have to leave
Okay.
things there. Let's thank